Chapter 10, Properties of Solids and Liquids, Section 10.1, Electron Dot Formulas. Go and watch video problem 51, and you'll see some more Lewis structures here. So electron dot formulas, another term for this is Lewis structures. Alright, and basically what they show is how all the atoms are connected in a covalent bond. Okay, so we're mainly talking about covalently bonded molecules here. And what they show are the bonding pairs, which are the electrons that are being shared between atoms, and then the lone pair electrons. Okay, and those would be electrons that are not shared between atoms. So you should remember back to valence electrons for single atoms. So the alkali metals have one valence electron. The alkaline earth metals have two. Boron family, carbon family, nitrogen family, oxygen family, the halogens, and the noble gases, except helium, which has two dots there. Okay? So this is all based off of the idea that all atoms, they're going to share electrons so that they have stable, low energy, and all of their orbitals are filled, right? So they're all looking to get an S2p6, and the reason why they want an S2p6, or the reason why they attain, I shouldn't say they want, the reason why they attain an S2p6 is because it's stable, and by stable what we usually mean is lower energy. Okay? So we use a series of steps in order to write these Lewis dot structures, and I'll walk through the steps. In the video problems I go through the steps as well. But what we want to do is first identify the central atom. So in other words, what atom is going to go in the middle? Okay, typically it's the one that we have less of. There are generally a couple rules here. The carbon always goes in the middle. And then from there, it's typically, so carbon always goes in the middle, or it's typically the least electronegative element, which we haven't really talked about yet. We'll talk about that in the next section. I'm not going to be able to fit that in there. Okay? So first, get the central atom. Second, you want to count up the total number of valence electrons from all atoms. So just write out the atoms and how many valence electrons each atom contributes. Surround the central atom with the other atoms. Then connect all of those atoms with dashes, and each dash represents a single covalent bond, which a single covalent bond is a sharing of electrons. So that is a shared pair of electrons, or as we set up here, it's a bonding pair. Now the next step then is to give all atoms an octet 8 except hydrogen. Hydrogen 100% of the time will have a dash. And then finally what you need to do is compare the electrons that you're showing versus the electrons that you counted in step 2, the valence electrons. If they're equal, you're done. Good Lewis structuring. If you have too many on the structure, you got to make double or triple bonds. Now in AP, you'll talk about what if you have too few. What if you're showing too few? In other words, you should have more shown. But for now, we're just going to stick with making double or triple bonds. So I'm going to break with tradition here. I'm going to go ahead and go through one of these. I'm going to go through this phosphorus trichloride just so you can sort of see the steps. Okay? Matter of fact, I'm going to grab these steps and bring them down with me. So let me see if I can do that without too much of a problem here. I don't like that one. I cut off the numbers. There we go. That's better. Alright, so let's come on down here. Let's see if it'll let me paste it right here. It did not. Okay. We'll just go through them. I know what they are. Okay. Step number 1, identify the central atom. Look, it's PCl3. So what do you think is going to go in the middle? Phosphorus. Ooh, that's a big. So phosphorus is going to go in the middle. Okay. Now the next step is to count up the total number of valence electrons. So let's see. Phosphorus contributes 5 valence electrons. Each chlorine contributes 7. So that's a total of 26 valence electrons. Okay, so that's step 1 and step 2. Step 3 is to surround that central atom. So I'm going to do a chlorine. So here, let me just real quick. What you do is imagine that this phosphorus is in a box. Okay, and there's 4 sides to that box. So we can put the dashes or the bonds on those 4 sides. Now, later on, we'll call each one of these areas an electron domain, and that idea is pretty important, electron domains. So what we're really doing here is we're showing an electron domain. So there's an electron domain, chlorine. There's an electron domain, chlorine. There's an electron domain, chlorine. Okay, so I surround it with central atoms. Now I'm going to go around and give everybody 8. So right now, this chlorine right here has 2. Right? Because that dash, that's a single covalent bond. Okay, so that represents 2 electrons. Right? So that's 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. So now all those chlorines have 8. Look at phosphorus, 2, 4, 6, and then I'm going to put 2 more. There's 8. Okay? So I went around and made sure everybody had 8. Now my next step is to count up how many electrons I'm showing on the structure versus how many I'm supposed to be showing. So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So I'm showing 26. I'm supposed to be showing 26, so I'm done. So let's take a look at this. All right. So I counted off the electron domains. So let's look at them again. So here's 1 electron domain, 2 electron domains, 3 electron domains, 4 electron domains. So this particular structure has 4 electron domains. Again, that's going to be important later on. Okay. I'm trying to erase my highlighting. All right. Now let's talk about this covalent bonding here in this structure altogether. All right. Erasing everything as I go along here. So, all right. Look right here. Here's chlorine. It has 2, 4, 6, 8. So that chlorine has 8 electrons in its outer shell now, which is an S2P6. That's stable, which means lower energy. Take a look at this chlorine. 2, 4, 6, 8. That has 8. 2, 4, 6, 8. That has 8. But look at the phosphorus. 2, 4, 6, 8. That has 8. So by sharing the valence electrons, which is a covalent bond, by sharing the valence electrons, they all have a full s and p orbital, which is stable with lower energy. So it's advantageous for them to bond. That's why they form a covalent bond, to lower the energy, which is more stable. Okay? Let's see. Let's do this one real quick just so I can talk about the electron domains. All right? So I'm just going to whip through this. Why don't you pause it and try it yourself with CO2, and then I'll go through it here. All right. So I'm going to put carbon in the middle. All right? I'm going to count up the total number of valence electrons, 4 for carbon. Each oxygen contributes 6. So that's 12. So that's 16 electrons that I'm dealing with here. Single bond O, single bond O. Now let's go around and give everybody 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. So there we go. Now I got to count up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. But I'm only supposed to show 16. So this is where I got to make double bonds. So I'm going to come back and make a bond here. Take off 2 electrons and 2 electrons. So that's 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6. Everybody has 8 still. And if I count up, now I'm showing 18. So I make a double bond, And let's take a second here. Notice that I made a double bond there, right? So now this carbon has 2, 4, 6, 8, 10, and it can't do that. It can't have 10. So I'm going to take those off. Look at this oxygen, 2, 4, 6, 8, 10. Well, it can't do that, so I got to take 2 off. So now everybody has 8. 2, 4, 6, 8. 2, 4, 6, 8. All right. So there I just made a couple double bonds. I'm showing 16. I'm supposed to be showing 16. Now this Lewis structure has 2 electron domains. Okay. So in other words, 2 sides of the box, quote unquote box, are being used, which we can equate that to 2 electron domains. Again, this is going to be important for the next section. All right. Now, Lewis structures are pretty good. They're pretty good at predicting how things are bonded, okay, at the actual molecule. But sometimes Lewis structures don't work. For instance, in the case of resonance. So if a molecule has double or triple bonds, then a lot of times you can draw more than one formula. So here, take a look at this. Let me number these. These are 1, 2, 3. So that's oxygen 1, oxygen 2, and oxygen 3. Here's 1, 2, 3. All right. So notice you can draw 2 different structures here. You can draw one where the double bond is between oxygen 1 and 2, or you can draw one where the double bond is between oxygen 2 and 3. Now remember, those are 3 completely different oxygens. Okay. So which one is right? Well, experimental evidence tells us they're both right. So here's the deal. A double bond is a certain length, okay? A double bond is actually shorter than a single bond. And this is when we're looking at length. Right? So the double bond is shorter than a single bond. So when we measure the distance between this oxygen and this oxygen, 1 and 2, versus oxygens 2 and 3, we should see that oxygen 1, 2 is closer than oxygen 2, 3. But we don't. What we actually see is that oxygen 1, 2 is at the same length as oxygen 2, 3. And neither one of those is a single or double bond length. It's somewhere between a single and a double bond. So that implies that both of these structures exist at the same time, because it's a double bond length and it's a single bond length at the same time. And that's what resonance structures show us. And that's why they were introduced, in order to correct that problem. Okay. Now, just to let you know, there are exceptions to the octet rule. For instance, boron. Boron can take less than an octet. Beryllium can actually form a covalent structure and take less than an octet. And then also the halogens on the 3rd through 7th period can take more than an octet. Now, I'm not going to go over that here. I usually go over that in AP, so I'll save it for that. But just realize that there are some exceptions.